Oh, okay, it doesn't matter. So for the brain, you will have this behavior. When you do simple shear. Need to supply sigma 2,2. Oh, wait. Yeah. And sigma 2,2 is negative. So, yes, to counter that, so sorry, sigma 2,2. Yeah, you need to push down here. Bulging out. You need C2 must be. So remember we had a constant shear modulus. We had a straight line, so it meant it was either New-Hookian or Mooney-Rivlin. Well, both of them will work. New-Hookian doesn't work. You need I2 dependence. Bulging out means that C2 is positive, which we had assumed anyway. Now, if you were able to measure sigma 2,2, then you will have access to C2. It's very difficult. Well, I'm still working on it. I haven't seen much literature on that. At least we can find C1 plus C2 by measuring the slope of the straight line. And then finding C1 and C2 separately is more difficult. But you can still learn a lot from just looking at the experimental data. And then finally, let's look at the forces on the slanted faces. Slanted faces here. So here we'll have two vectors, and we've done that before, the normal vector and the tangential vector. And we found that they were like this: 1 minus k0 and t the unit vector tangent to that face is k10. So if I want to compute, say, the tangential, the shear stress, tau, it's going to be T minus Tn. I just want to compute that. I could see that's going to be 1 over k squared, k10, 111, 121. Well, it's symmetric anyway, so it doesn't matter. I'm just computing this quantity here, 1 minus k0. So it's going to be plus k squared times k10 times sigma 11 minus k sigma 12, sigma 12 minus k sigma 22, and 0. And now this dot product is going to be 1 over 1 plus k squared times sigma 11k minus sigma 12k squared plus sigma 12 minus k sigma 22. And now I can regroup things. I'm going to have sigma 11 minus sigma 22k plus 1 minus k squared sigma 12. And then sigma 11 minus sigma 22, I had that from my universal relation here. It's k sigma 12. K sigma 12 times k. And I can see that the k squared terms are going to cancel out. Tau equals sigma 12 over 1 plus k squared. And so tau cannot be 0. And what that tells you, and you can also compute sigma, the normal stress. What is it? It's going to be n sigma to n. And you will find this quantity here. Again, it's not a 0 quantity, right? The second part cannot be 0. And so it means that you need to supply forces on the slanted faces. And if you don't, well, then you can't achieve simple shear. You'll end up with something like this. You'll end up with bent slanted faces. They're not straight anymore. And that happens when the material is just, you know, actually it happens all the time when it's not supported on the faces. So that's why I try to do that with the shear box. But the shear box is not simple shear because it's shearing but also compressing a little bit. If you wanted to do that, if you wanted to apply plates on the side, you will have to have plates that will, you know, extend somehow as they follow the side of the sample. Quite difficult to imagine. Forces must be supplied to maintain the simple shear. So what the protocol standard tell you is to minimize that effect by having a material that's thin, right, like a rectangle, so that those effects are going to be localized near the edges, and then by and large inside the material it's going to be homogeneous deformation and close to simple shear. Okay, I've gone over by 3 minutes, so I better stop now. But I'm happy to take questions if you have any. And in any case, we meet again on Wednesday for my final lecture. After that, Pepe will take over for the final 2 weeks. Any questions? No? I stop recording.